What lies between the stars? Is it pure emptiness or is there something lurking there? In this lecture, I'll discuss what lives in the space between the stars and why this wispy material has great importance to astronomers and how it makes all those amazing images you see on astrophotographers' websites. Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. This time we're going to be talking about the interstellar medium, the space between the stars, or that which fills the space between the stars. The thing when we say medium, we don't mean like medium like television or radio or something like that, or the interwebs. No, we mean the gas and dust that is between the stars that fills, or at least gently fills, the space between it. Most of the space in the Milky Way between the stars is filled with a very thin gas, and it's mostly made up of atomic hydrogen gas, which makes up most of it. However, there's bunches of deep, dense clouds that fill up most of the mass of the gas of the galaxy, but not much of the actual volume, and those are the deep molecular clouds. Then we find young stars in hot gas regions where stars are forming, and the light and intensity from that energetic light is so intense that it actually ionizes the gas. So we have different flavors of the gas between the stars. So we'll call those are the three phases of the interstellar medium. We'll say ISM for short. And the interstellar medium itself is composed of three rough phases, and this came about through studies that started in the 1970s. And the first phase is what we'll call the cold neutral media. And, again, with the word media, meaning the thing that through which the thing that is transmitting data, or at least is holding the data, which is kind of a weird way of thinking about it. It's the medium of the material between the stars. And so we're going to talk about neutral hydrogen, which is what we call H1. That's not high. It is H with the Roman numeral 1, and that means it is neutral and not ionized hydrogen. And then there's H2, which is the molecular hydrogen, or two atoms of hydrogen bound together in a molecule, as well as molecular clouds, meaning very small diatomic or triatomic molecules that make up a significant fraction of it. The temperature of these gas clouds are very low, just above absolute zero, and they're also some of the densest spots. And dense is kind of a weird word here, because when we say dense, when we think only 100 to 1,000,000 particles per cubic centimeter, that still is a much better vacuum than we can do anywhere in any laboratory on Earth by factors of many billions. So these regions, though, that have this density they take up only about 1% of the volume of the Milky Way, but yet they concentrate almost most of the mass of the Milky Way. In fact, that's a significant fraction of it. In fact, there's more material in these cold, dense clouds than there are in the stars. Then we have the next phase, which we'll call warm, neutral, or ionized media. And this is either hot, ionized H2 regions, meaning there's one electron that's been liberated from the atom, and so now it's H2. And then there's still H1, which is neutral hydrogen. And they reside near star formation regions where stars are heating the gas and making it warm, and the temperatures range between 6,000 Kelvin and about 12,000 Kelvin, and that's what glows. And so the densities are a lot less than the dense clouds, where you can even have only one particle for every 100 cubic centimeters. And the typical size for a cubic centimeter is that of a sugar cube. So imagine that a sugar cube, 100 sugar cubes stacked around each other, and there's only one atom inside that volume. That is an enormously good vacuum, but still, that's what we see when we look at these glowing clouds. Those are areas where we have this enormous glow, and you might think, oh, there's a lot of stuff there. No, it's almost completely rarefied. It's just that the areas are so incredibly large, and there is so much about them that they glow enough that you can see that, but the actual densities of the areas that are doing the glowing are extraordinarily low. So they're very thin, and we would call it warm, but that would be pretty hot to us if you went over there and went and just actually sampled that gas. And finally, there's another interesting area called the hot ionized media, which is strictly ionized, and it emits in X-rays. emits an X-ray light, and it's composed primarily of hydrogen, but it also is composed of ionized heavier elements such as iron and nickel and so forth. And they're the hottest zones of the Milky Way, and they make up the bulk of the volume of the interstellar medium. But they make up the bulk of the volume, but they don't make up the bulk of the mass, which is interesting. So they spread out because they're so hot, and the temperatures range between 1,000,000 and 10 million Kelvin and can be observed in X-rays. They're extraordinarily thin because they only have like 1/10,000th or 1/100th of a particle per cubic centimeter. So now you got to line up 10,000 sugar cubes in order to get one particle instead of just 100 like before. And these regions are made up by, when you have a supernova type star explosion, they'll shock the gas into heat, and then it'll heat it to that temperatures, and then they'll rise up out of the plane of the Milky Way, just like we see in the top image, and that makes up what we call the galactic corona. And so this is evident when we look at the Milky Way later. We're going to see pictures of the Milky Way where we have X-ray emission. In fact, let's go take a look at those. So the Milky Way in optical light shows us some of the interstellar medium. We see not just the starry background and some of the stars above and below, but we see dark clouds that obscure our view of the center of the Milky Way, and that obscuration is dust and gas in the way. But if we look in, say, hydrogen emission from 21 centimeter radiation, and 21 centimeter radiation occurs when a neutral hydrogen atom, the electron in it changes from spin up to spin down, and that's a very, very, very tiny amount of energy, but yet it emits it in radio frequencies at a wavelength of 21 centimeters. And we can see that the radio frequencies of 21 centimeters tends to be strongly collimated across the plane of the Milky Way, with some diffuse clouds going above and below. And so the height, we call it a scale height of the Milky Way, is very, very low and confined. So the cold dense media is confined to the plane of the Milky Way quite aggressively. And then we can see how it mirrors with respect to, say, carbon monoxide emission. So CO is 2 atoms. It's a molecular gas called carbon monoxide. Don't breathe it. Not good. Get out of the house if there's carbon monoxide poisoning. You know what that's like. But so there's carbon monoxide all throughout the Milky Way. That's really bad, I guess, but we're not going out and breathing that, so no big deal. Anyway, so we see these are clouds of carbon monoxide, which also radiate in microwave wavelengths, and this is a map of those gases taken by the European Space Agency's Planck probe. But the carbon monoxide is used as a tracer for the molecular hydrogen, which doesn't emit pretty much anything that is easily observed. So molecular hydrogen, but carbon monoxide gives a much better tracer of it. And we know that there's a lot more molecular hydrogen near where the carbon monoxide is. So we use that as a tracer. Now if we look at the hotter media, which is the H-alpha, which is ionized hydrogen gases, we start to see that there's puffy glows all over the place, and it's not necessarily directly confined to the plane of the Milky Way like this 21 centimeter radiation is. And these are places where we call star formation. So this is hot interstellar media with the temperatures approximately 8,000 or so degrees or 10,000 degrees Kelvin. Next we have in X-rays, which demonstrates the galactic corona. We see these huge bubbles and loops of gas that go above and below. So you can see that they go way high, and this is from the Rosat satellite. And this is what we mean by it occupies a much larger volume. It's not confined to the Milky Way. It looks like it's well above and below. So other places that we can see the effect of the interstellar medium. And now it's pretty picture time. And this is the most fun, one of the most wonderful elements of looking at star formation that we're going to talk about in the next few lectures, is the pretty pictures. And this is the North American Nebula off to the left. And the North American Nebula this is a visible light image compiled by DeMartin, but it draws from the Digital Sky Survey, the Palomar Digital Sky Survey. And you can just make color images of it if you go download that stuff. On the right-hand side, though, is from the Spitzer Space Telescope, which looks in the infrared at multiple wavelengths and shows emission of dust, emission of warm dust, cold dust, and gas. And so in infrared, it looks different than it looks in visible light because we're looking at different processes. And we see the dark band that goes across the middle of the nebula. It corresponds to actually some warm, dusty clouds in infrared. So that dark band is actually warm dust. And if we look where the North America sort of feature is on the left, we see it doesn't really glow much in infrared, and that's because it's hot ionized hydrogen gas, which is warm, so it's not going to glow in infrared because it's too warm for that. So we have four different views of that, one of them in visible and infrared combined. So this was done by Spitzer Space Telescope Group at NASA Jet Propulsion Laboratory, and they just put this together to help you see the views. So here is a combined view of the Digital Sky Survey infrared with the Spitzer image, and we see the dusty appearance of the reddish dust cloud that goes across the middle, and now the bluish glow is then, they've replaced the pink of hydrogen with the blue with a bluish glow. But that highlights the dusty cloud. So now we get to see the dust in the background, which is very interesting because that shows us where stars are being formed. And then we look specifically at a different wavelength that shows us the interior of the clouds, and we get to see different aspects of it. And then it's being blocked. We see a little tiny nodule in the center left where it's dense enough that actually we don't see anything through it. And finally, we get to see that dense star-forming region that's in the lower left that highlights that very tiny baby stars, which are like little points in red. And that's what we're looking at here, is the highlighting that specific area of looking at young stars being formed in a very, very, very dense molecular cloud. That's what I was talking about at the beginning, where we were talking about very dense, small regions. This is a much more massive region because it's collapsing and forming stars. The other region is much larger around it, but it's much more rarefied. And so this is a dense, highly dense region and surrounded by a hotter, more rarefied, thin region. And so when we look at that, we have all sorts of things that we can see. And so let's focus in on the nature of what happens when we try to observe those dark areas. And interstellar matter is mostly just gas and dust. And what's funny is that we think, oh, it's just really complex sort of cloudy structure, there's all sorts of stuff. What is that? No, it's really actually quite simple. The clouds are turbulent, they move around, they're warm or cold, but they're mostly almost completely hydrogen. Remember, it's 75% hydrogen, about 25% helium, and all the rest is just really, really, really trace amounts. But this cloud that we're looking at, Barnard 68, is a dust, and the dust that we talk about is actually like soot or smoke, and the larger clumps of particles are really quite tiny. The dust particles that make up this are about the same size as cigarette smoke and are only composed of a few hundred or a few thousand atoms. And so why does something so small actually make the starlight behind it black? Well, it's because there's a lot of it. So this is a beautiful picture by the European Space Agency, European Southern Observatory, that actually highlights a very interesting feature called interstellar reddening. So in the center of this dust cloud, all the light is being blocked. But if we look on the edges of the dust cloud, we see that some of the stars look red. And the reason that they look red is because as the light passes from behind stars through the dust cloud, it preferentially absorbs and scatters the blue light of the spectrum. So we're left with the red light, and so it looks like it's making the stars red, but it's not actually making the stars red, it's actually just simply removing the blue light, and so we just see the red light. And why we think about that is that compare the stars that seem very red on the edges of the cloud compared to the red stars that are away from the cloud, and we see that those red stars are really bright. So we're looking maybe at some some very extraordinarily bright red stars on the far side, but their light would be brighter except that it's being dimmed and the blue light is being removed. And if we look in longer wavelengths of light, meaning infrared, we can see more through it because infrared light will pass through this dust and gas, pass by this dust. In fact, the wavelengths of infrared are longer than the size of the particles, and since they're longer than the size of the particles, they're not affected by the particles, and so they pass through. And now we can see it's like the dust cloud isn't even there, or at least it's ghostly. So this is a longer wavelength view by the European Southern Observatory. And finally, we can look at various wavelengths of light, starting from in the upper left at that's 0.044 microns, or specifically that would be 4,400 angstroms. So that's well inside the visible light, and that's on the far blue end of the spectrum, so we see that it's all gone, right? And then we look at 0.55 microns, which is 5,500 angstroms, which is more bluish. and or more greenish in the visible light, but it's blocking that too. Now then we get out to 9,000 angstroms, well red of visible light red, we see that the cloud looks kind of smaller, and that's 0.90 angstroms, micrometers in the upper right. And for some bizarre reason, they decided to go around rather than go back to the left and around. So go down and to the right at 1.25 microns, which is then 12,500 angstroms. And that's very long wavelength infrared light, or at least the beginnings of near infrared. And now the light is getting through, and we look at 1.65 micron, and it's really starting to get through. But by the time we get to 2.16 microns, which is 21,000 angstroms, the light's pretty much getting all the way through, and the dust cloud is not even being seen by that wavelength. It just kind of passes through it. It's the same kind of way that the light is passing through because it's large wavelength, in the same way that when you take a set of like little, if you take a beach ball and roll it across a whole bunch of little pebbles, it won't see the pebbles. It'll see it's like a roll, about like a whole bunch of pebbles. The beach ball will roll across a thin level of pebbles, just smoothly. But now if you try to roll a pebble across a roll of pebbles that's about the same size, it'll get bounced around as you roll it across. In the same way, the wavelengths of light, the long wavelengths are like a big beach ball going across the pebbles. It just doesn't see them. It doesn't perceive them. And so that's what the 2.16 micron is. But when we look at the 0.44 right above it, that's like looking at wavelengths of light that are almost the same size as the particles themselves, so they really get bounced around as they go through, and so therefore they get absorbed and you don't see through it, so they get lost. All right. So that effect is called interstellar reddening, and we described that extensively. But what we see is it got the cloud, the starlight's coming from behind it, it goes through it, and as it goes through it, this light gets scattered or absorbed, and the stellar absorption lines stay the same wavelength, but all the blue light just gets removed. And so you can still tell the stellar type, the stellar spectral type, like we talked about spectral types before, but the stellar spectral type is not changed. You just lose a lot of the light. So you might think it's a redder star, like, oh, it's an M-type star because they're red. No, but look at the absorption lines. They're the absorption lines of a bright blue star. So the blue light is just being absorbed away. And that's called interstellar reddening or interstellar extinction. And interstellar extinction is something you see when you look at a sunset. And that reddening that you see in the sky is because the sun's light, the reason you can look at a sunset and the sun looks red is because the blue light gets scattered away from your eye, and so all you're left with is the red. And the reason that you have a blue sky during the day is because someone else has a red sunset. And that blue light in the sky is from all the sunlight from being scattered around the sky, because blue light is easily scattered. And in fact, the particles in the Earth's atmosphere are about the same size as blue wavelengths of light. So the exact same process is going on in the Earth's atmosphere with respect to clouds and just the atmosphere itself, where blue light is easily scattered and red light not so much because it's longer wavelength. And so that's why we have a nice blue sky, is because of all the pretty sunsets all across the globe, everywhere. So here's some really cool interstellar scattering demonstrations. We have Barnard 68, that one that we were talking about a while ago, for extensively. But then you got the really cool Snake Nebula, and these two are right next to each other in the sky. And this is from the Palomar Digital Sky Survey, and we're looking in the blue. We took this is a picture from the blue filter on the blue emulsion filter set from Digital Sky Survey. And if we look at another one, this is another one called the Pipe Nebula. There's all sorts of wonderful darkness. And it used to be thought that these things were holes in space, or maybe there were no more stars in that direction. And in fact, people thought that this was like the edge of the galaxy or something, but past that there was nothing. And that was an early thought of early astronomers doing photographic studies of dark nebulae like these. And they ended up just being dark nebulae, not the edge of the galaxy. And a good friend of mine who did a major set of studies, his name was Bart Bok. And Bart Bok was thought that back in the 1950s and 1940s, he published a paper in 1947 hypothesizing that these things were actually gravitationally collapsing, and this is where stars would form. And so they're called Bach globules. And Bart Bach was a friend of mine when I was a little boy. And he said, "You've got to come down to der Kit Peak and see der stars." And he was this wonderful Dutchman, big old hairy eyebrows, and they stuck out everywhere. He was a wonderful man. He used to like to have a bottle of scotch and yell at radio astronomers. That was one of his favorite things to do. Anyway, Bart was known as one of the great observational astronomers, and these globules still keep his name today as places where over dense regions where stars are forming. And one of the more prominent Bach globules, actually more, it's not really a globule, it is a dark dust cloud. The Horsehead Nebula shows off this and demonstrates many aspects of the interstellar medium. It has cold areas, it has hot areas, and it has extraordinarily hot areas, as well as dark cold areas as well. So the pink glow is from hydrogen, and it's hot and heated to excitation by nearby very hot stars. But you can see that there's a dark nebula, which is the Horsehead Nebula, dead center, and there's also dark nebulae off to the side that seem to be providing some of that interstellar extinction. You can see the clouds of gas around it, which seem to block some of the background light. We also see the Flame Nebula off to the left there, below below these lights, and these stars are all part of the Orion Belt. And so, if you went and looked at Orion's belt, you would definitely you could actually see some of these things. So I invite you to go look at some of the nebulae surrounding Orion's belt. But let's zoom in on the Horsehead Nebula itself, because it's one of the more prominent dark nebulae in the sky, and it has such a wonderful name, and it's been studied extensively by lots of different people. And here is a picture of it by Adam Block at Mount Lemmon Sky Center at University of Arizona, which really highlights the hydrogen gas, which is interesting. You notice those wispy streamers in the background as it evaporates off. And we also have a different kind of nebulae, which is a blue nebula. And in fact, it's the same stuff. It's a reflection nebula, and the light is reflecting off of it. But the Horsehead Nebula is, even if we zoom in even tighter, we see some really interesting features of these cloud-like structures, and it's actually in motion. So it does look turbulent. It looks like it's actually plowing upward and above and turning over. But when the size scales are on the order of light years, so this isn't moving like fast, although it is moving with some great speed, maybe tens or hundreds of kilometers per second. If not, maybe not even that fast. But I can't remember the actual study, but that might be something as a good assignment to go look up. How fast are the clouds moving in the Horsehead Nebula? In any event, the pink hydrogen glow in the background it illuminates the Horsehead Nebula. But very recently, the Hubble Space Telescope took a look at the same object in infrared, and this is the view in the infrared that was released in 2013. And when we look in infrared imagery, we now then see the cloud of gas and dust as warm dust that's glowing in infrared. But yet the hydrogen gas doesn't glow in infrared, and all of a sudden we can see through the veil of it to see everything in the background. And now we see the Horsehead Nebula not as a horsehead, but as a turbulent cloud that's coming up out of the clouds below it, and an overdense region where things are occurring. So if we then we can then take a stronger view of it, and this is an interesting movie, a fly through done, I believe, by Frank Summers at Space Telescope, to actually try to dimensionalize it and 3Dize the view of the Horsehead Nebula as what it might look like if we were flying at it at, much faster than the speed of light, I can tell you, because this thing is on the order of half a light year or so in size, where light years is its size scale. We can see all sorts of little tiny red dots, and those are very tiny red dwarf stars in formation around it. So what are some things that we can learn about specifically about the nature of these dust dark clouds? On the left-hand side, we see the view in optical, then the infrared view, a longer infrared view, we see some other stuff. And then if we look in radio light, which is the carbon monoxide 3-2 transition, which is a transition, I believe, either as a vibrational transition or a rotational transition of the carbon monoxide atoms. And it's such long wavelengths that it only emits those things and these are tiny transitions in light, rather than the atoms jumping up and down, the electrons jumping up and down. Basically, they're either vibrating faster or slower, or rotating faster or slower. And that's what the radio emissions from. And the submillimeter radio emission on the right-hand side shows overdense regions where stars are forming. And so we can look at these cold molecular clouds as either contoured maps with maybe even much more exotic sorts of things, which are hydrogen, carbon monoxide, smaller molecules of 4 atoms that are bound together. And those emit in radio wavelengths as well. And so it's kind of, we find interstellar water as well as other things. And some molecules such as ethyl alcohol have been found, formaldehyde has been found. Long organic molecules have also been found by their signatures in radio frequencies, and these appear in these giant molecular clouds. I know it's talking about the neutral hydrogen, or H1 regions, and this is what we mean by that spin-flip transition. The proton and electron can be spinning with the same orientation for their spins. And this is kind of a weird way of talking because they really don't spin like this, like little balls, but there's a quantum number that approximates angular momentum, or it actually is the angular momentum, as though it has a spin axis. And then when this spin-flip transition occurs, the photon that gets emitted when the electron jumps or flips and goes, they spin the opposite direction, is a lower energy state and emits 21 centimeter radiation. We can make large maps of the Milky Way doing that. And in fact, there's a carbon monoxide map of a tighter view, as we saw from the WISE spacecraft before. And we're going to kind of get close to finishing it out by looking at some other wonderful images, because this is the pretty picture lecture, and we're looking at dark globules, and it's a Bach globule because Bart, Big Bart with his scotch and his eyebrows. He would love to have looked at this in the Spitzer image, but he passed away well before in the 1980s. So wonderful old man who gave us a tradition of looking at the star formation regions and looking at the galaxy in its whole. And here's another example of a dark dust cloud with a hot region with an H2 region sitting in the middle of it. So this is what we're going to be looking at with the interstellar medium, and we're going to be looking at all sorts of aspects of the interstellar medium and exactly how stars form from the interstellar medium, protostars, giant molecular clouds, and we'll talk about that stuff next time. And we'll see you soon.